Welcome back to our course on memory device technology for AI/ML computing. Let's do a quick recap of what we were discussing in the last lecture. We saw how the noise margins in both read and hold operation depends primarily on the size of the hysteretic butterfly loops. More precisely, it depends on what is the size of the maximum square or the side of the maximum square that you can fit inside the butterfly loops. Okay, so this is what we saw the last time. The second thing that we primarily looked at was that as we were scaling the supply voltage of the transistor, or we were scaling the supply voltage of the SRAM cell, the size of the hysteretic loops or the butterfly VTC loops were shrinking, as you can see from the red to the magenta to the green color, and as a result the noise margins were also coming down. This is what we had seen also in this graph, and of course there was a way to kind of counteract this reduction in noise margins with supply voltage, that is to improve the cell ratio. So if you improve the cell ratio, the voltage disturbance on the internal node reduces a little bit, and this gives you a benefit of improved noise margins. But we will see in today's class that indiscriminately increasing the cell ratio is not always a viable solution, and this is because what I have been hinting throughout the SRAM section, that the design requirements for read and write are actually at loggerheads, and this is what we will discuss today. What are the conflicting requirements for both read and write? Okay, just a quick recap. Whenever we were studying about the read, write or hold operations, we were trying to understand the SRAM operation or SRAM cell using this intuitive picture of a W-shaped potential barrier. And we discussed that if the height of this barrier, which is separating these two stable points or these stable configurations, is very high, if this barrier, energy barrier, is very high, indeed you will get a little bit of higher noise stability in hold and read operation, but writing will become very difficult, right? And if the barrier is too low, then of course write easeability will improve, but the stability during read and hold will become worse. Now, whatever I am explaining intuitively in terms of words, when you can be very easily explained from the perspective of the SRAM cell when you look at the design perspective. And if you look at the competing requirements for cell ratio and pull ratio, things become very clear. Remember, the cell ratio was introduced to make sure that your read operation is inherently non-destructive. I've explained it several times, so I will not repeat it again. By ensuring that the strength of the PDMOS is much higher than that of the PGMOS, you can ensure that delta V dash, or the disturbance during this read operation where a small I read current flows, this delta V dash can be minimized, and therefore this read will be non-destructive. On the other hand, the pull ratio was what was determining, or which was improving the flipping of the bit from 1 to 0 during the write operation, right? This was big, and this was ensured by making sure that the strength of the PGMOS transistor or the access transistor, the strength of the PG NMOS transistor was much larger compared to the strength of the PU or the pull-up PMOS transistor. If you ensure that the value at N2 will very easily flip from 1 to 0 because BL bar was charged to 0. Okay. Now, when we put the requirements of NMOS and the PMOS, when we put the requirements for cell ratio and pull ratio, the design or the transistor sizing requirements for cell ratio and pull ratio together, we see that the relationship is that the strength of the PD NMOS should be greater than that of the PG NMOS, which should be greater than the pull-up PMOS. Now, immediately, as you can see, that there is a big problem in trying to accommodate both good cell ratio and good pull ratio. And that is the fact that if the strength of PD NMOS and the strength of pull-up PMOS in the inverter structure is very disbalanced, as this equation seems to suggest, this will create problems in your noise margin. Why? Go back to one lecture back. We had seen that if there is a unbalance in the inverter design, or the strength of NMOS is greater than PMOS, one of the hysteretic loops or one of the butterfly loops will shrink considerably. And as a result, since the maximum size of square that you can fill in the smaller hysteretic loop will also come down, and this will compromise the noise margins. So a natural question to ask is, how do we solve these conflicting read and write requirements? Okay, so it becomes more like a chicken and egg problem, because remember, in the previous slide we saw that in order to have good noise margins, you need to ensure high cell ratio, but the moment you start having higher cell ratio, you start seeing disbalance in the inverter, which in turn then compromises the noise margin. So how do we solve this chicken and egg problem? There are two key approaches in trying to come up with a viable solution. The first is by using biasing schemes for the 60 SRAM cell, which are slightly modified from what we have been studying. And the second approach is to modify the structure of the 60 SRAM cell itself. So let's start by discussing the biasing schemes first. So in the biasing schemes, the idea is you will have the same 60 SRAM cell that we have been studying till now, but during read and write schemes, you deviate slightly in the biasing methodology to ensure that during read cycle, read happens more easily, and during write cycle, write happens more easily. So therefore, the biasing scheme is in turn divided into read assist and write assist cycles. Remember, these are not two different cells. They are different biasing schemes which are applied on the same SRAM cell, one during read and another during write. So let's first look at the read assist scheme. So what was the key philosophy of having the read assist scheme, or what did we want during read assist? We wanted to make sure that a good cell ratio is maintained. The beta or cell ratio is the strength of the pull down transistor must be greater than the pass gate transistor. So an artificial way, I would say, of ensuring that during read operation, the pass gate transistor has slightly smaller strength is by ensuring that you do not assert the word line which is connected to the gate terminal of the pass gate transistor to complete VDD. So as you can see in the schematic, which has been pointed out in green, the VDD is put in dashed lines, whereas during read assist, the word line is indeed asserted. You turn on the pass gate transistor, but the voltage that you apply during the pulse is slightly smaller than VDD. How does that help? It helps because remember the on state resistance or the current during on state is proportional to VGS minus VTH. Okay, so if you reduce VGS minus VTH by reducing VGS, you will be able to reduce the drive current. If you reduce the drive current, the drive strength automatically comes down, and therefore artificially during biasing you are able to maintain a large cell ratio by making sure that the strength of PG1 is reduced by having smaller gate biasing. Now, of course, this will have its own set of problems or disadvantages, and the first immediate disadvantage that we can think of is, remember that during the non-destructive read, a read current flows from the bit line through the pass gate transistor and pull down transistor into the ground terminal. Now remember, this read current will now encounter more on state resistance from the pass gate transistor because you have reduced the gate voltage, and as a result the parasitics the parasitic path to the pass gate transistor will increase, and this will result in lower read speeds. Okay, so this is what you have to deal with when you try to artificially increase the cell ratio by biasing schemes. Next, we move on to the write assist scheme. In the write assist scheme, what you essentially recognize is that the initiation of the write assist scheme, as we had studied 2 lectures back, is from the storage node which contains the value 1. So in write assist scheme, instead of having the bit line corresponding to the storage node which had a value of 1 grounded or to be deasserted to 0, you use a negative bit line value. So use, suppose, minus 0.2 volts, minus 0.3 volts. Now, how does that help? Now, compared to your original biasing scheme where bit line was 0 and this was VDD, the internal node was VDD. Now, where the potential difference was just VDD, now you have a higher potential difference. Why? Because the bit line has been asserted to a negative bit line value. And as a result, the bit flip from 1 to 0 will become easier and it will become faster. But there are no free lunches in life. So the disadvantage that we have to generally deal with is that the biasing circuitry, so generating negative voltages is not always very easy. It is easy, but it will come at the cost of increased biasing and peripheral circuitry. We have seen in our previous classes how important it is to maintain a small peripheral area in order to increase the memory efficiency. Okay, so these are the first set of solution which involves specialized biasing schemes for read and write operations. The second solution is to completely revamp or completely change the structure of the 60 SRAM cell. And the core idea over here is, since read and write had conflicting requirements, why don't we completely decouple read and write through different parts in the circuitry? And this is what I will explain through one example of the 80 SRAM cell. Now, there are several examples of 70 SRAM, 80, 10T, 90 SRAM cells, but I'm taking the example of this particular 80 SRAM cells because they are now being routinely used in the sub 45 nanometer node in order to improve noise margins and stability. Okay, so let us look at the structure of this 80 SRAM cell. It appears to be very complicated, but let me tell you that the core part is still the 60 SRAM cell. So this is the core 60 SRAM cell. As you can see, there are a few additions which are made to the 60 SRAM cell, and this is what I will now quickly mark out with red color. So the differences from the original 60 SRAM cell is this new read word line, new read bit line, and couple of added transistors, transistor M7 and M8. Okay, so the operation of the 80 SRAM cell is fairly simple. If you look at it, the write operation is exactly identical as the 60 SRAM cell. So you have your write bit line and you have your write bit line bar and you have your write word line. So the write operation is absolutely identical to the 60 SRAM cell. But what you have decoupled and how you are decoupling by adding 2 extra read word lines and read bit lines and 2 extra transistors is you are completely decoupling the read operation. And how do you decouple the read operation? You do it by connecting the internal voltage node, here indicated by W. You can call it Q. You can call it Q or you can call it VN1, to capacitively coupling it with another transistor called M7. Now, when the value of Q is 1, because M7 is an NMOS, it is turned on, and when you apply a read enable at the RWL, both these transistors M7 and M8 turn on, and as a result the read bit line, which has an original value of VDD, can be discharged. So if there is a discharge in the read bit line when the read word line is enabled, we know that the value at Q, which is connected to the gate of M7, is 1. If there is no discharge, we know that the value of Q is 0. Now, the interesting thing that I want you to pause and think very carefully about is, why did we make this very interesting design choice of keeping the write operation same as 60 and only making a difference in the read operation? Let me repeat the question. In this entire diagram of 80 SRAM cell, what you have done is the write operation is identical to that of the 60 SRAM cell, only the read operation have been separated out. Why has that been done? Why has it not been the opposite? Why didn't you decouple write separately, and why wasn't the read part of the circuitry kept same, and why didn't you make a new circuitry for write? So think very carefully. There is a very important lesson to be learnt over here. So the answer to my question, why read was completely decoupled, is because that if you see the new read operation, the earlier read operation, there was a read current which was flowing through M1 and M4, like we have been discussing several times. And this flowing of this read current caused a disturbance, internal disturbance to this value in the internal node Q. Now, this resistive I read current has been completely removed in the new structure, because Q has been capacitively coupled to the gate of M7 transistor. And once it is capacitively coupled to gate of M7 transistor, even during read operation, there is no current which actually flows through this internal node Q, and therefore there is no read disturbance. And since there is no read disturbance, your noise margins, your read noise margins are as close as your hold noise margins. And therefore you get much better read noise margins even at smaller operating voltages. And since you are able to reduce VDD, even 80 SRAM cells have lesser power consumption. Okay, because you are able to scale the VDD without compromising on noise margins. However, the disadvantage, of course, is that you have added 2 extra transistors and 2 extra lines, the read bit line and the read word line, and therefore the area scalability goes a little bit out of toss, right? But as I discussed, there are no free lunches. In order to improve some metrics, in this case you are trying to improve the read noise margin and the power consumption, you have to make certain sacrifices by adding little bit more footprint area. Okay, so this is how you are trying to circumvent using 2 different techniques, both biasing schemes and AT-SRAM cell, the problem of conflicting read and write requirements. Okay, so the last part of our discussion on SRAM cell, with which we will conclude, is this brief review of the technological innovations which are driving improved performance in SRAM cells. Okay, so recall that we had already discussed all this in detail earlier in our course, where we were discussing how innovation drives the global memory market. At the time, we discussed, since SRAM cells are constructed primarily from the same transistors that constitute your advanced technology nodes, SRAM innovation is primarily driven by 2 factors. The first factor is transistor scaling. So anybody who has taken a basic course in semiconductor devices will know what transistor scaling is. Transistor scaling is the phenomena where reducing the channel dimensions of the transistor or the form factor of the transistor gives you multifold benefits in terms of area scalability, cost, power consumption, speed, etc., etc. And anybody who has done a basic course on VLSI technology or CMOS processing technology will know that transistor scaling has been only enabled through extreme lithography. So nowadays we are in the 3rd generation of nanolithography, where we are able to print really tiny dimensions using extreme UV lithography. Okay, now the benefits that transistor scaling have derived from individual transistor performance have derived from both these aspects of transistor scaling technology and extreme lithography have actually been transferred over even in the SRAM technology, and therefore SRAM technology has become a technology qualifier for any advanced technology nodes. What does that mean? We will discuss in the next slide. Before that, let us discuss how transistor scaling has helped the SRAM performance. I think this we had discussed already, so I will try to go a little quickly. As you know, as you increase the technology nodes, the individual transistor length or the channel length starts shrinking from 180 nanometers to 90 to so on and so forth, to currently we are even in the era of sub 10 nanometer technology node. Once you reduce the size of an individual transistor, from the perspective of a SRAM cell, the contacted gate pitch also starts coming down exponentially. So the Moore's law suggests that the contacted gate pitch is reducing, or the lateral dimensions is reducing by 0.7x every 18 months or 2 years. What is this contacted gate pitch? Contacted gate pitch is the gap between 2 adjacent transistor. It consists of the gate length of the transistor, the contact width, and 2 times the spacer. The spacer is the gap between the gate finger and the contact. Okay, so when you add this LG plus WC plus 2 W spacer, you get the contacted gate pitch. And since contacted gate pitch is a linear dimension, if that is reducing by 0.7x every 18 months or 2 years, you can understand that the SRAM cell size will increase by 1 by 0.7 the whole square. And therefore, what is essentially happening is the SRAM cell size is reducing by half every 2 years. And we are seeing really important developments in the SRAM in the SRAM performance, because you are able to fit more and more SRAM cells in a smaller area, because the area or the cell size is improving by twice every 18 months or 2 years. However, with the advent of the 22 nanometer technology, two tectonic shifts happened in SRAM technology. The first thing what you might notice is, for the first time, the size of the SRAM cell reduced or went below 0.1 micrometer square. So in 32 nanometer node, the previous technology node, the minimum size of the SRAM cell was 0.171 micrometer square. However, with the 22 nanometer node, at least in the high density cell, you were able to cross over to less than 0.1 micrometer square. That is just one of the advantage. The second advantage, as you can see from this figure, in the 22 nanometer node, unlike previous generations, you could have different cell libraries for SRAM cell. The high density cell, the standard cell, and the high speed cell, which optimizes for area or it optimizes for speed. We have been seeing throughout that once you try to improve speed, you have to compromise on area and vice versa. So my question to you, pause the video, do a little bit of Googling and see what was that remarkable shift that happened from the 32 nanometer node to 22 nanometer node that enabled these two very interesting things to happen. So some of you might know that what essentially happened from 32 to 22 nanometer node is that the planar transistor moved to a FinFET design. And as you can see from the structures of the high density cell, standard cell, and high speed cell, by selecting the number of fins, by deciding how many fins you are including in the SRAM cell, you can control the area. Larger number of fins will give you larger area, but also it will give you larger drive current. So a high speed cell will have larger area because of larger drive current and smaller parasitics. However, a high density cell will comprise of only one or two fins of the FinFET technology, therefore compromising on speed. Okay, so these are the point I'm trying to essentially make is the improvements in transistor technology really push the flexibility and performance of SRAM to a different level. However, it is important to know that the normalized area, what is our normalized area? Recall when we were studying memory footprint, we were normalizing everything to f squared, where f was the smallest dimension. Although with improving technology nodes, indeed the bit cell is reducing from 0.092 micrometer square to 0.021 micrometer square. However, when we normalize it with f squared, f is the smallest feature of that particular node, we see that the benefits of area scaling or size scaling are really diminishing, because the normalized area to f squared is increasing from 190/300 to almost 840 f squared. So although we are able to reduce the dimensions of an individual transistor, it is not giving equivalent benefits in reducing the cell size of your SRAM cell, and that has got to do primarily with routing constraints. So you need to also route the signal appropriately. Okay, so the last thing that we will study for our SRAM portion is how SRAM is being used as a technology qualifier. Remember what was technology qualifier? Since SRAMs are made from these high advanced technology nodes, whenever a new transistor technology node is developed, the 60 SRAM cell array is fabricated using that technology node, and by doing multiple read and write operation test cases, you try to see how well your SRAM is performing and therefore how well your transistor technology is also performing. And this is done by this technique called Shmoo plots. Shmoo plots, where what you do is you do these pass-fail tests. So what you do is you take a bunch of data, you write into an SRAM array, and then you read it back, and you do it across different voltages and across different frequency. As you see, each small dot over here, each small box is the same test performed at different frequencies and at different voltages. And what we essentially see is we see this very beautiful pattern of pass and fail. Of course, as you can understand, at higher frequencies, you will be requiring higher operational voltages. This is because at higher frequencies, you would want your transistor to respond much faster. And how do you respond much faster? By applying higher drive current. Okay. Another very interesting thing to notice over here is the fails in the low voltage and the high frequency, the failures which are happening in the low voltage regime and the high frequency regime are entirely different in nature. Whereas the read failures are more likely to happen in the low voltage or low VDD, write failures are more likely to happen in the high frequency regime. Why is this the case? You can see in the slides, while read failures happen primarily because of violations to the read noise margin. And remember, read noise margin was very sensitive to low supply voltage, whereas write failures happen because your propagation delay is now becoming comparable to the pulse of the operation frequency of your write transactions. Therefore, write failures are more likely to happen for high frequencies. Okay. So with this, we will conclude our SRAM section. I hope you enjoyed the SRAM section, which was quite extensive. We looked at several aspects, both fundamental and technological. Next class, we will begin with the DRAM cell. Thank you very much.